I'm Stephen A. Edwards. Our Sparse Synchronous model arose from a colleague's need to precisely specify the behavioral experiments he conducts on rats. That's him there in the shirt. In particular, he wanted to precisely measure their reaction times to various stimuli. These experiments are usually conducted by writing some very specialized C code for a microcontroller, which is difficult, non-portable, and makes it difficult for others to reproduce the experiments. Here's a typical task taken from one of his papers. He plays some odd sounds to the rats, which tells them whether to look for a reward in the left or the right port. Then he waits a little while before giving them the reward. The science is in how long the rats wait before giving up if they got it wrong. The problem is that existing solutions, such as C on a microcontroller, are ad hoc at best. A library function like sleep is very imprecise. Something like a real-time operating system provides more control, but tends to be even less portable and predictable. What's really annoying is that the typical microcontroller has a timer accurate to at least a microsecond, yet they are hard to use. So we set out to develop a language capable of describing such temporal behavior that relied on microcontroller timers for reproducibility. Here's what we have so far. We start with a traditional imperative language, add the ability to make concurrent function calls, and, most importantly, make it possible to assign variables at a precise time in the future and to stop and wait for those variable updates. Here's the hello world of the microcontroller world. Blink an LED with a period of 100 milliseconds. Compiling and running this example gives us a waveform with a period of exactly 100 milliseconds, even though the processor is taking an unknown amount of time to send an output to the LED and schedule itself to run again later. One of our basic tricks is to only expose model time to the programmer, who thinks the program is running on an infinitely fast processor. It's the job of our runtime system to maintain this fiction. We primarily rely on the microcontroller's timer for this, which runs at the same rate regardless of processor load. Our runtime system is built around two queues. The ready queue holds routines that are scheduled to execute in the current time instant. These are prioritized according to their location in the program, which ensures deterministic execution. The event queue holds future variable updates. In each instant, the runtime updates the variable scheduled for the current time, then runs the routines in the ready queue that were triggered by these updates. When the runtime is done for an instant, it sets its alarm clock to when the next variable is scheduled to be updated and sleeps. While sleeping, it can also be awakened by events from the environment, which also update variables and trigger routines. We're currently working on a more elaborate language and compiler based on this model.